come to the first video lessons of basis and dimension of a vector space under PMAT 21553. So in this lesson, we will discuss what is a basis and dimension of a vector space, some properties of basis, and how to find out the basis for a given vector space. First, we will go through the definition of a basis. If we have a set S in a vector space V, we call it a basis if the following conditions are true. So if we have a set S sub vector space V, we should have a subset of V, we denote by it S, and it contains point vectors V1, V2, Vn, and S has two properties. S spans V. So that means if you take any vector V from the vector space, we should be able to write as a linear combination of these vectors. So that means any vector V in the vector space should be able to write as a linear combination of the vectors V1, V2, Vn. And the second property is S is linearly independent. So that means if you take a linear combination of the vectors in S, if it is equal to 0, then all coefficients should be equal to 0. So that means if we have, A1, V1, A2, V2, and so on, AN, Vn is equal to 0. All the coefficients A1, A2, An should be equal to 0. If these two properties hold, we call the subset S of the vector space V is a basis for the vector space V. Two properties, S spans V and S is linearly independent. Okay, now look at this example. Show that the following set is a basis for R3. So in R3, we know that it should contain three components in a vector. Now we have considered a set containing the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. First of all, we have to prove that S spans R3. So that means if you take any vector of R3, we should be able to write this vector as a linear combination of given vectors. So just consider any point, any vector containing three components x, y, z. Now, so x, y, z. Now you can write clearly, taking x out and keeping other things 0. So x times 1, 0, 0, and plus y times 0, 1, 0, and z 0, 0, 1. Now that means, so these are our given vector in S. So that means any vector of the vector space can be written as a linear combination of the vectors in S. So this implies S spans R3. So S spans R3. Now, as a second condition, we have to prove that S is a linearly independent set. So for that purpose, we take a linear combination into 0. Now, if it is linearly independent, we should have all A, B, C should be 0. Clearly, from this equation, you can set up two equations considering the first component. You get A is equal to 0, A equals 0. Considering the second component, you get B is equal to 0. Considering the third component, you get C is equal to 0. So that means all A, B, C are equal to 0. So therefore, S is linearly independent set. So S spans R3 and it is a linearly independent set. So therefore, by the definition of a basis, it is a basis for R3. Now, what we have considered 1 0 0 0 1 0 0 0 1. So we have three positions usually in a component. So for first one, we have 1 here and they are 0 0. So we usually denote it E1 in R3. 0 1 0. 1 is moving from starting from 1 to the other component. So this is known as E2 for the vector space 0 0 1. So this is denoted by E3. So there we call it is a standard basis for R3. Standard basis for R3. For R3 it should have three components. So three vectors with first position 1. The other components are 0. It is known as E1. Second position it is 1. Other components are 0. E2. And third component is 1. Other components are 0. That is E3. So this is a standard basis for R3. Very similarly, we can consider standard basis for Rn. So it should have n component. E1 is the first place, it is 1. Other components are 0. For the E2, second component is 1. Other component are 0. Likewise, if I say EI, so that means component are 0 and in the ith position it is 1. And other component are all are 0. It contains in components ith positions are is 1. Ith position is 1. All other components are 0. So this is called standard basis for Rn. For example, if you consider R4, it should have four components E1. So 1 0 0, E2 0 1 0 0, E3 0 0 1 0, E4 0 0 0 1. So this is a standard basis for R4. Standard basis for R4. Okay, now we have one example. Show that the set B is a basis for R3. So we in the previous example we have discussed the standard basis for R3. Now this is also, so we have to prove that this is also a basis for R3. So to prove that B is a basis, we have to prove that it spans R3. So B spans R3 and the sets in B are linearly independent. So first we consider any component of R3 as ABC R3 and we try to write down this ABC as a linear combination of given vectors. So C1 1 0 plus C2 1 1 1 second one, C3 0 1 minus 1 third vector. Now we want to prove that if this is now one can say that it's a system, it is a set of equation containing C1 C2 C3. Now you can write down the corresponding system. So you get C1 plus C2 is equal to A, C1 plus C2 plus C3 is equal to B, and C2 plus is minus C3 is equal to C. So it's a system of linear equation. If the system of linear equation has a unique solution, so in that case we can claim that the set spans R3. So now So this is the augmented matrix corresponding to the system of linear equation. Now you can reduce by using the row operations to this matrix. So for example, you can say if you want to prove that, you may remember the row, how to convert row echelon form. So you can make this one into 0 by multiplying by this one and adding it. This operation is multiply the first row by r minus 1 and add into third row or second row. So this will be your new um, second row. So then you get what you here you get the first row doesn't change, and the second row 0 0 1 b minus a, and 0 1 minus 1 c. Now so we have to make this one into 1. We can interchange with r2 and r3. So you can see 1 1 0 a 0 1 minus 1 c. Here you have 0 0 1 b minus a. So one may feel this is in reduced row echelon form, but to make it little easier, sorry. So we can I can add r2 and r3 as r3. So r2. So new second row will be you multiply the third row by 1 and add into the second row. Then you get 1 1 0 a 0 1. So this will be 0 then. So you add b minus a into c. b minus c b minus a. So the here 0 0 1 b minus a. Then you can multiply the second row by minus 1 and add into the first row. So multiply the second row by minus 1 and add into first row. So this will be your new first row. Then you have 1 0 0. So multiplying the second row by a, you get by minus 1. So you have plus a 2a minus b minus c. So 0 1 0 c plus b minus a 0 0 1 b minus a. So that's how we perform the convert into Jordan Gaussian elimination process. Gauss-Jordan elimination process. You start with the augmented matrix, convert A into identity matrix, apply the same operations into left hand side, then you will get this matrix. From there you can write equivalent system. System has a unique solution because number of non-zero rows is the same as the number of variables c1 c2 c3. From there you can calculate c1 as 2a minus 2a minus b minus c, c2 minus a plus b plus c, c3 is equal to minus a plus b. So system has a unique solution. So that means B spans R3. B spans R3. Now, first we have proved that it is B spans R3. Now we want to prove that it is a linear. When you take the linear combination into 0, then you have it is linear independent. So that means when you take a linear combination of vectors in B, we should be able to prove that they are um, all the coefficients are equal to 0. So what I can do it here, you take C1 110 plus C2 111 plus C3 times 0 1 minus 1. If this is equal to 0, then uh, if all the coefficients are equal to 0, C1, C2, C3 are equal to 0, then you can claim it is linearly independent. C1, C2 is equal to 0. So C1 plus C2 plus C3 is equal to 0. Then you have C2 plus C3 is equal to 0. Now, if you take these two equations, you can say C1 plus C2 is equal to 0. So that means this term is equal to 0. So then you get C3 is equal to 0. Whenever C3 is equal to 0, from the third equation, you can get C2 is also equal to 0. From this equation, you substitute C3 is equal to 0. Then you get C2 is equal to 0. When C2 is equal to 0, you can go to the first equation, substitute C2 is equal to 0. You can get C1 is equal to 0. So either you can use this simple calculation because set of equation is very simple, or you can go to the solving the system of linear equation. You can prove that all C1, C2, C3 are equal to 0. Or one can say that this is a homogeneous equation. If the coefficients of the determinant uh, determinant of the coefficient matrix is non-zero, then it has a unique solution. It is a trivial solution, zero solution. So therefore, all coefficients C1, C2, C3 are equal to 0. So either way, you will prove that component in B are linearly independent. So therefore, B spans R3 and the component in B are linearly independent. So therefore, you can claim B form a basis for R3. B is a basis for R3. In the previous example, you have seen that standard basis 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this is the basis for R3, same vector space. Now we have proved that this new set in 1, 1, 0, 1, 1, 1, and 0, 1, minus 1 is also a basis for R3 for the same vector space. So what you can notice here, for the same vector space, there might be more than one basis, So that means basis of a vector space is not unique. So there might be different bases for the same vector space. Now, P3 set of polynomials of degree 3. So you may remember how to write it set of polynomial of in P3. So usually A0, A1x, A2x squared plus A3 S3 polynomial of degree 3. It has a basis, so we want to prove that it has the basis with the component 1x, x squared and x3. So first of all, we have to prove that S spans P3. So that means any uh, component, any polynomial of degree 3 can be written as a linear combination of 1, x, x squared and x3, where A0, A1, A2 and A3 are real numbers. So that means since taking the linear combination of the vectors S, we can write down any polynomial of degree 3. So that means we can claim S spans P3. Now, the next step we have to prove that the component in S is linearly independent. Component in S are linearly independent. For that, we have to consider zero polynomial. So that means whenever all coefficients a0, a1, a2, a3 are 0, we have polynomial x, zero polynomial. Now, if any combination is equal to 0, then we have to prove that a0, a1, a2, a3 are equal to 0. So clearly you can get it because you can consider the coefficients of x, x0, x squared and x3, then you will get you all are 0. For example, when you take the coefficients of x0, here you have a0. A0 is equal to, there is no constant term in the right hand side. A0 is 0. The coefficients of x, a1 again equal to 0. Coefficients of x squared again a2 equal to 0. Coefficients of x3 again a3, they are equal to 0. All coefficients of 1, x, x squared and x3 are 0. So therefore you can claim it is linearly independent. Okay. So if a polynomial is identically equal to 0, so that means all coefficients should be equal to 0. A0, A1, A2, A3 are equal to 0. So S is linearly independent. So S spans are P3 and it is linearly independent. So therefore, it is a basis for P3. Basis for P3. Now, in this case, we have taken 4 vectors 1, x, x squared, x3. So it is called standard basis for P3. Standard basis for R3. So that means if we have a polynomial in general, we can generalize this result standard basis for Pn. So that it's a polynomial of degree n. So basis for this is 1 x x squared until xn. For example, P4 polynomial of degree 3, the basis is 1 x x squared and x3 and x4. So this is known as standard basis for P4. Standard for P3 is end up with x3. Standard basis for P4 end up with x4. Standard basis for Pn end up with xn. So that's how we find the standard basis for polynomial vector space of degree n. Now we have a theorem. It says that uniqueness of basis representation. So that means if S is v1, v2, vn is a base for a vector space, then every vector in V can be written in one and only one way as a linear combination of vectors in A. You know that if S is a basis, so then it should span V. So therefore, any vector V can be written as a linear combination of S. So this representation, linear combination is unique. There is no two possibility to write the same vector. So how to prove that? Since S is a basis for the vector space, it spans V and S is linearly independent. So then, since S spans V, any vector in vector U in V can be written as a linear combination of S. Suppose this is U. U can be written as two ways. One is U is equal to C1 V1 plus C2 V2 and so on Cn Vn. The other possibility we propose, U can be same vector U can be written V1 V1 plus V2 V2 plus and so on Bn Vn. So if this U has a unique representation, So if we want to claim that it has only one representation, so that means we have to prove that C1 is equal to B1, C2 is equal to B2, and so on. Cn is equal to Bn. The coefficients of B1, B2, V3, Vn are equal. So how we can do that? Just consider you and me, u minus u, then you get like 0. So in the right hand side, C1 minus B1 times V1 plus C2 minus V2 times V2 and so on. Now we know that V1, V2, Vn, they are linearly independent. So when the linear combination is equal to 0, all coefficients should be equal to 0. So that means you get C1 is equal to B1, C2 is equal to B2 and so on. Cn is equal to Bn. So if we have two representation for the same vector u, these two representation in terms of Ci Vi and C2 V2, both they are is to be Pi. So in this case, Ai is equal to Bi. So that means same representation. So the representation is unique. We have only one representation for the basis S. Now consider this example. Suppose U is U1, U2, U3 be any vector in R3. So we want to prove that, show that the equation U, C1, V1, C2, V2, C3, V3 has a unique solution. So that means this, when you write down U as a linear combination, U as a linear combination of V1, V2, V3, then it is unique. So here V1, V2, V3 are given by this vector. So to prove that, we take a linear combination. So U1, U2, U3 is written as a linear combination of given vectors V1, V2 and V3. From there, you can get, you can simplify this C1 plus C2 0 minus 2C3. So the first component is C1 minus C1 minus 2C3. Second component 2 times C1 plus C2 plus 0 times C3. So that means 2C1 plus C2. 3C1 plus 2C2 plus C3, third component. Now, from this equation, we can get a system of linear equation. The first component, equating the first component, C1 minus 2C3 equal to U1. 2C2 plus C2 is equal to U2. From the third component, you get 3C1 plus 2C2 plus C3 is equal to U3. Now it is a system of linear equation. You can write down the augmented matrix and show that it is as a unique solution. To show that it has a unique solution, you have to prove either you can take the determinant of the coefficient matrix and show that it is equal to 0, or you can use the row operations and you can show that it has uh, 3 variables and 3 non-zero rows. So so you can write down in matrix form, and then you can calculate the determinant of A. So this is the coefficient matrix. When the determinant is not equal to 0, you can claim that the system has a unique solution. So when you calculate the determinants, you get 1 into 1, 1 minus 0 here. With 0, you don't get anything. 2 into 1 minus 0, 3. And minus 2, 2 into 2 is 4. Minus 1 into 3, minus 3. So the value of the determinant is minus 1. So determinant of A is not equal to 0. So that means it has a unique solution. Or to calculate the values of C1, C2, C3, there are several possibilities. You can calculate the inverse of the matrix A. So I am not going to discuss how to find out the inverse matrix. You may remember in the first year in the matrix algebra course, we discussed how to find out the inverse of a matrix. So when you calculate the matrix A inverse exists because it has a unique determinant of A is not equal to 0. Now to find out we have the matrix representation A C is equal to B U. So you can multiply both sides by A inverse, then you get C is equal to A inverse U. So you get you know the value C1 A inverse, value of A inverse and U. So C1 C2 C3 is equal to A inverse. We have already 1 minus 2, 2 minus 7, 4 minus 1, 2 minus 1, and U1, U2, U3. From there you can calculate C1, C2 and C1, C2 and C3. Okay. So it has a unique solution, unique representation, and the representation is determined by in terms of U1, U2, U3. Okay. Now we go to the next theorem, basis and linear dependence. So if S is a basis, S containing the vectors v1, v2, vn is a basis for the vector space, then every set containing more than n vectors in V is linearly dependent. Linearly dependent. So it is like something like that. If you have the set basis v1, v2, vn. So this is our basis. If you consider any other set containing more than n vectors, it's not necessary to be S to be a subset of S. So if you have one more element, let's say V, so then this set, let's say S1 is linearly dependent. Linearly dependent. If you have more vectors, if you have any vector, any set containing more than n vectors, then it is linearly dependent. So how to prove that? Suppose x1 contain u1, u2, un. If m is larger than n, so we want to prove that S1 is linearly dependent. S1 is linearly dependent because m is larger than n, it contains more vectors than n, so therefore it should be. So we want to prove that it is linearly dependent. To prove that it is linearly dependent, so we want to prove that when we take a linear combination into 0, so we have to prove that at least one component linearly dependent. So we want to prove that at least one component are not equal to 0. It should be not zeros. It should be not zeros. Not. We will show that all k1, k2, kn are not zeros. So that means at least one coefficient is not equal to 0. Now, so from the previous case, k1 u1 plus k2 u2 km un, we know that since v1, v1, v2, vn, so it is a basis for the vector space. Since it is the vector basis for the vector space, any vector u1, u2, u3, all vectors this um can be written as a linear combination of v1, v2, vn. So u1 can be written as a linear combination of v1, v2, and vn. u2 can be written as a linear combination, and so on. All can be written as a linear combination of v1, v2, vn. So we consider the coefficients for u1, c11, c21, and so on. For the u2, c12, c22, cn2, and so on. Now, since we have taken the linear combination is equal to 0, we can replace this u1, u2, from these representation. then you have replace V1, replace V1 in, then you have K1 times C11 V1 plus C21 V2 and so on, and then you can rearrange taking the component V1, V2 and Vn. Okay, you can simplify into this. So what we have done, we substitute U1, U2 and Um from this combination, from this representation, and rearrange such that take the coefficients of V1, V2 and V3 and Vn, so on. Now you know that V1, V2, Vn, this set V1, V2, Vn is a basis for the set vector space. Since it is a basis, it is linearly independent. So if it is, since it is linearly independent, when you take the linear combination into 0, so all coefficients, so this coefficients, this one should be equal to 0, this one should be equal to 0, and this should be equal to 0. So therefore we have system of linear equation, homogeneous system of linear equation. Now you know that it has how many variables? K1, K2, K3, Kn, m variables. And how many equations? Starting with 1, 2, and the last one is n. So n equations. So number of variables, m is larger than number of equations. So number of variables larger than number of equations. So in that case, a system of linear equation has infinitely many solutions. It is homogeneous system and in a linear equation of m variables. Since the number of equation is less than the number of variables, it has infinitely many solutions. So since it has infinitely many solutions, you can have k1 is equal to something, k2 is equal to something. It has a infinitely many solution. At least one solution contain non-zero value for some k1, k2 or kn. So that means it is a linearly independent solution. So what we have to take from here, if a basis Vn, a basis contain n elements, n vectors, any other vectors more than n element is linearly dependent. Linearly dependent. So that's the message from this theorem. Now consider this example. You know that R3 in we have discussed two bases. So all contains three vectors. So basis for R3 has three vectors. Now if you consider any set of vectors more than three vectors, 1, 2, 3, 4. So since it contains number of vectors more than the number of vectors in the basis, so it is linearly dependent. So one more example, P3. You may remember the standard basis 1, x, x squared, x3. So it has four vectors. The set S must be linearly dependent because it has 1, 2, 3, 4, 5. 5 vectors. So it's more than 4 vectors. So therefore it is linearly dependent. So now the next things we discuss, number of vectors in a basis. If a vector V has one basis with n vectors, then every basis for V has n vectors. So for the same vector space, there might be more than one basis, but it all bases of the vector space contains equal number of vectors. So if we has n vectors, any other basis, every basis for a V has n vectors. Let's see how to prove that. Suppose we have two bases. One is containing V1, V2, Vn in vectors. The other one S2 is also basis U1, U2, Um. Suppose we have m vectors. So idea is to prove that it has the same number of vectors. So we want to prove that m is equal to m. N is equal to m. Now we know that S1 is a basis. So since S1 is a basis and it is linearly independent, S1 is linearly independent. We know that S2 is also linearly independent because it is also basis. So therefore, number of vectors in containing in X2 should be less than n. So because m should be less than no n because S2 is linearly dependent. If S2 contain more than n elements, S2 should be linearly dependent. But since it is a basis, it cannot be linearly dependent. Only possibility is S2 should be linearly independent. So that means the number of vectors in S2 should be less than or equal the number of vectors in S1. So we have m is less than n2. Similar argument we can carry it out very similarly. S2 is basis, so therefore it is also linearly independent. Any other vector, any other linearly independent vector should contain less or equal number of vectors as S2. So S1 is a linearly independent vector because it is also basis. So the number of vectors in S1 should be less than or equal number of vectors in is 2. So therefore, n should be less than or equal. So in the first case, we have m is less than or equal. The second case, we have n is less than or equal m. So that means n should be equal to m. So any basis for a same vector space contain same number of vectors. Now we want to prove that this is not a basis. So it contains only two vectors. If R3 has R3 has three vectors because you may remember E1, E2, E3. So the number of elements in the basis is equal to 3. So but for S1 we have only two vectors, so it cannot be a basis for R3. Here x plus 2, x squared, x3 minus 1, 3x plus 1, x squared minus 2 plus 1. How many vectors? 1, 2, 3, 4, 5. 5 vectors. 5 vectors in S2, but we know that for P3 it should contain only 4 vectors, 4 elements. So therefore, this is also not a basis for P3. Since a basis of P3 has only 4 vectors, any set more than 4 vectors cannot be a basis. S2 contains 5 vectors, so it cannot be a basis. So what we have discussed in this lesson, the definition of basis of a vector space and some properties of uh, basis of a vector space. For more details, you can go through this recommended reading. It is given in the your course schedule. So in the next lessons, I will discuss we will define the dimension of a vector space and some properties of basis and dimension. Thank you so much for joining with us.